So, greetings. Now let's just move on with this beam picking problem. And I mentioned that we will prove things on the competitive ratios of the algorithms which I listed last time. And for this particular problem we don't use the very same notion of competitive ratio than the one we used before. So when studying actually the beam picking problem, well, we don't use, well, at least for this particular lecture, this particular course, we don't use the competitive ratio as before, the very same competitive ratio. So it's not the same competitive ratio as before, but the so-called asymptotic I'm just writing this here, asymptotic competitive ratio. So it's called this way, asymptotic competitive ratio, and it's again, I'm having an algorithm A. I run this algorithm on an input, okay, and then I just divide by the optimal cost. For that particular input. That's fine. That was the competitive ratio, just taking the supreme. And I mentioned that it's not always, so in not all the cases we have an actual maximum value, but it might be the supreme value for all possible inputs. So that was the so-called absolute competitive ratio, which we use all the time so far. But now we are just considering this ratio for long enough inputs, or not long, but or it's just inputs having an optimum value larger than some threshold. So I'm just computing this fraction only for those sigmas for which the optimum value is at least some value, and then I'm taking the limit of these suprema if n tends to infinite. So this is basically just simulating if the what can I say about the ratio if I know that the optimum value is large enough. So that's what is modeled. So basically, if you just run the algorithm on a possibly infinite or very long input sequence, then what you can say about the ratio of the algorithm and the optimum cost. So basically this formula doesn't really care about short inputs ratios. So that's the asymptotic competitive ratio which we will deal with. And now, so let's just move this here. Okay. Now this means that if we want to prove and of course we do want to prove it. So if you want to prove that an online problem doesn't have say a deterministic online algorithm, with an asymptotic ratio smaller than c. And this is the difference. So with an asymptotic competitive ratio, better than C, or I would say it's better than C. Okay. So what's this? It's a lower bound. So this is a sort of result saying that for this particular program there is no algorithm. There is no algorithm which is better than C, competitive for some C. So previously we created bad enough inputs, say 2 of them or 3 of them, one of them being a prefix of the other one, and prove that an deterministic algorithm behaves badly either on the first one or on the second one. And we just computed 2 ratios and taking the maximum of these. So if we want to do this, so then we still have to provide, provide bad inputs and show that any deterministic online algorithm behaves badly at least one of them, That's the same as we've done before, with a difference, but now we have to construct bad inputs for each n, and today we will learn this. So we have to construct such inputs say sigma 1, sigma 2 and so on for each n, so that the optimum value for each of these inputs is at least n. Why? Because in the formula we had here, in order to be able to use these inputs for fixed n, I will have to construct an input having an optimal value larger than n, at least n. Now let's see this in action. Let's see this. Let's do this. So for the bin packing problem, So for this problem, this goes as follows. So for each n, I will have to construct inputs, and so that each deterministic algorithm will behave badly on at least one of these inputs. And previously, we always defined inputs which were prefixes of each other, and this doesn't change, so it's a good choice to create inputs being prefixes of each other. So let's say that let's fix n. So it's just larger than 0, is just a number. Okay. So that's an integer. And let us define the first input, the shorter one, to be 0.4, 0.4, 0.4, and so on. 0.4. How many? 2 times n items. Now, of course, the optimum for this particular sequence is n, because you can pack 2 of these guys into one single bin, but not 3. So the optimum value is n. Now that's great. I have to construct an input for which the optimum is at least this fixed integer n. And for each n, I have to be able to construct such an input. And let's say sigma 2, and again it will start by sigma 1, and then I will have a number of items of size 0.6. So I started by items of size 0.4, and then I finished the sequence by items of size 0.6, again 2 of them. Now the optimum for this case is 2n, right? So for to reach the optimum n, I'll have to pack these 2 items into the same bin. So I will have n such bins, but for the sigma 2, I will have to pack an item of size 0.4 and an item of size 0.6 into a single bin, and to create n such bins. Now again, the situation is that if the input happens to be sigma 1, I will have to do a very different action sequence than if the input is the word sigma 2, because in the first case, in the shorter case, I should pack these 0.4s into one bin, 2 of them, and in the second case I should just pack the 0.4s in each separate bins, but I don't know in advance whether those 0.6s arrive or not. Okay, so that's good because it's at least n, so that's also good because it's at least n. Fine. Now let's see how a deterministic algorithm can process the sigma 2. Let's see how deterministic online algorithm can process sigma 2. Again, as before, we are just making here a case analysis, and for each case the action sequence, the response sequence on the sigma 1 prefix will be determined by the sigma 2's action sequence. Sigma 2. So at the end of the processing, say, binning processing, we can have say it's quite possible that at the end there will be a bin having a single item of size 0.4, or a bin can contain two such items. Or a bin can contain one item of size 0.4 and one item of size 0.6. Or, option 4, the bin can contain a single item 0.6. But those are the only possibilities. So I cannot pack 3 items into a single bin, I cannot pack 2 0.6 items into a single bin, and so on. Now, let's say that at the end there are K1 such items, such bins, having exactly one item of size 0.4, and at the end let the algorithm produce a sequence, an action sequence, having K2 of those bins containing 2 0.4 items. That's K3 the number of these bins, and that's K4 denote the number of those bins. Now, the important thing is that these items containing at least one item of 0.4, so these were already used when I finished processing the first part of the input. So these bins were already used. When the algorithm finished processing the sigma 1. Now, which means that the algorithm's cost on sigma 1 is, because after processing all the items of size 0.4, I'm using all the bins of the first 3 types, it means that the output cost of the algorithm is K1 plus K2 plus K3 on the first part of the input, while on the whole input on sigma 2 we are using all of these bins, so it's K1 plus K2 plus K3 plus K4. Okay, and also the number of bins, the number of items in the bins is 2n, I believe, so there are 2n items of size 0.4, which means that at the end the total number of items of size 0.4 in these bins is 2n. So I also know that K1, because those bins contain one item of 0.4 of size 0.4 each, plus 2 times K2, because these items contain 2 of these items, so that's what the 2 coefficient is coming from, plus K3, so that's the total number of items of size 0.4. Now this guy is 2n, because the total number of items of size 0.4 is this value. And I also know that K3 plus K4 is also 2n, because that's the total number of items of size 0.6 at this input. Okay, and the ratio of the algorithm is at least the maximum of two values, the algorithm's cost divided by the optimum value, so it's k1 plus k2 plus k3 divided by n, because n was the optimum value for sigma 1. And the other case is k1 plus k2 plus k3 plus k4 divided by the optimum value for sigma 2, which is 2n. So what happened? So this is just a sigma 1 divided by the optimal cost for sigma 1, and this guy there is just a of sigma 2, the cost of the algorithm run on sigma 2, divided by the optimal cost for sigma 2. Yeah, and of course, since the ratio of the algorithm is the supremum of all the possible inputs for this ratio, for all the possible inputs having an optimal cost at least n, this means that these two are allowed and the supremum can be even larger, so the ratio is at least this guy. Now it's again, to get the optimal value for this one, I just have to solve a minimax optimization, which means that from this I will get the following things. So it's just k1 plus 2k2 plus k3 equals 2n. Yeah, it's okay, equals 2n. And then k3 plus k4, that's also equals 2n. And I have to minimize the maximum of these two things, which means that I have to say that okay, let's k1 plus k2 plus k3 divided by n is at most t. This is again introducing the new variable t, which will store the optimum value once we solve this system. k1 plus k2 plus k3 plus k4 divided by 2n is again at most t, and I want to minimize the t. Okay, now this is just a mechanic rewriting of the original statement. So that's the cost of the algorithm, that's divided by the optimum, that the cost divided by the second optimum, and these are just describing all the possible solutions. But in this case, the k1, k2, k3 and k4, these are integers, and an LP solver is not exactly good with integers, so we will do a relaxation. So we will just introduce the real variables. So it's not necessarily integer, it can be an arbitrary value, and at the same time introduce real valued variables xi. Let xi be the ki divided by n. Now if I just divide the first equality by n, I will get k1 divided by n, which is x1, but this time this is a real value, plus 2x2 plus x3 being equal to 2, and then I also have an x3 plus x4 also 2 if I'm just dividing by n, and k3 divided by n is x3, and k4 divided by n is x4. Okay, now as this k1 times divided by n plus this guy, so that's just the sum of the first three variables, x1 plus x2 plus x3 is at most t, and then for this I will get x1 half plus x2 half plus x4 half plus x4 half is at most t, and I have to minimize the t. Okay, now the key fact is this is just a relaxation of the original problem, because we can just have here for xi's arbitrary values, arbitrary real values, and while in the former case, in the integer case, I could have, say, 1 over n, 2 over n, 3 over n, 4 over n, and so on. So that was quantified. And here it's not quantified because I'm not stating that these should be integers or multiples of 1 over n, but this is a relaxation of the original problem. So we have a larger domain. But if this system has a larger domain and it's a minimization problem, then it means that this will be a lower bound for the original problem as well. So the value we get here is a lower bound for the original t. Okay. Now, but this is an LP problem. This is a linear programming problem. So if we just feed this system of inequalities to an LP solver, I'm pretty sure that you also have some other cores on which you are using LP solvers. The optimal solution says that t equals 4 over 3. And actually it also says that x1 is 0 and x2 is 2/3 and x3 is again 2/3 and x4 is 4 over 3, but this is just the optimal solutions place, sort of. But the important thing here is the t value. So again, for each possible algorithm A, we just proved that the minimum, the maximum of these two ratios here, the maximum is at least 4 over 3. And by this, we just proved that there is no deterministic online algorithm for bin packing with an asymptotic competitive ratio better than 4 over 3. It's better than 4 over 3. which means that I'm not able to construct, say, algorithms being 1.25 competitive and so on. But I might be able to create, say, a 1.7 competitive algorithm, because 1.7 is larger than 4/3. Now, this whole construct can be generalized, and this is what is called pattern sequences or packing patterns. So this whole approach right now, this 0.4 and the 2n times 2n and then 0.6 times 2n was a very arbitrary choice. Now we can play around. We can play around by other initial values. Other initial values, like defined by a sequence of pairs. Of pairs, say I have an item size A1 and some coefficient alpha 1. This is just a real number, positive real number. And then I will have A2, alpha 2, and so on. Some segments, say AK, alpha K, for, say, A1 and the others being item sizes, so between 0 and 1, and the alpha i's are simply just being positive. Such a sequence will denoting the following input sequence. Sigma 1 is just alpha 1 times n items of size A1. So that's where the alpha is used. It just describes the ratio between n and the number of items. And then sigma 2 is just sigma 1 followed by alpha 2 times n items of size A2, of course. Then the sigma 3 is just all the things we already used, and then alpha 3 times n items of size A3, and so on. Which means that we just used two such inputs. So previously we used the sequence. So we had, and I'm starting with the item size. So in the first group, the items had size 0.4, And then I had 2n of them, so alpha 1 was 2. And then in the second group there were items of size 0.6 and there were 2n of them. So we used the sequence before, It's this one. But I could create an arbitrary sequence and create a very similar linear programming problem from that. Which means how I do this. So for another sequence, so for an arbitrary other sequence, so I would say it's for a general sequence, arbitrary sequence, say A1 alpha 1, A2 alpha 2, and so on, AK alpha k. There can be more patterns, so after processing the longest input, say sigma k, but there is only a finite number of possible configurations again. So there will be there can be a finite number of so-called patterns. And that's how we are creating again a finite from some infinite thing. There can be a finite number of patterns. So let's denote the set P containing patterns like P1, P2, and so on, Pk. And how does it look like? It's just, it means that in a bin there is P1 units coming from the first segment, so P1 units of size A1, and then P2 units of items, P2 items of size A2, and P3 items of size A3, and so on. But of course all of these things only fit into a bin if the sum of the PIAI it's at most 1. And of course it won't be 0, because if it's all 0, then we don't use that bin. So the 0 vector is not the same as this one. So just to connect this with the previous example, so previously we had, so this set P contains pairs in that case, because there was 2 waves of input, the first wave containing items of size 0.4 and the second wave containing items of size 0.6. So for example, 1, 0 was a pattern, and 0, 1 was also a pattern, and 2, 0 was also a pattern, and 1, 1 was also a pattern. Basically this 1, 0 corresponds to those bins having 1 element from the first wave and 0 elements from the second waves. And the 0, 1 says that there is 0 elements from the first wave, but the one element from the second wave, and then the 2, 0 is just two elements from the first wave, and then the 1, 1 was just one element from the first wave and one element from the second wave. And that were all the options we had. In general, if there are many waves and the size are different, we have to we have to construct all the possible such vectors, such triples, such k-tuples, for which the total size of items fit into a bin. Okay, but this is just the very same inequality we get by just thinking. And then, okay, so there are a finite number of patterns, and we can write down inequalities. Let's see here. So, and then okay, and we can write inequalities like so total number of items from, say, wave I is alpha I times n. So I could write it the sum. So for each possible pattern, P1, Pk, so for each possible pattern, I'm just checking the number of these Pi's. Okay, so this means that this pattern uses Pi objects from the ith wave times, and I could write that ki for some integer I, for some integer value ki, and this should be alpha I times n. But again, this would lead us to some integer valued linear programming problem, which are hard. So that's why we are just again introducing variables x, and xi being just ki divided by n. And that way we just get, instead the previous one, we just get pi times xi. And again, xi is just ki divided by n, while ki is just it's just being the number of kp. Okay, I will just index. There is kxp, and this is p. This is a small p, not a capital one. So where kp is just the number of those bin configurations which are just in so those bin configurations corresponding to the pattern p at the end of processing the input sigma. Okay, and then there's and then there will be the optimization of t. Of t is just that, so the sum, so for each possible bin, p1 blah 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 pk, which is a pattern, and I will denote this vector by p, maybe underlining here as well, and here as well, here as well, and here as well. Okay, so it surely I have to count the number of some bins, but which bins? So for optimization of t, this was okay. In the previous case where I had only the 0.4s and the 0.6s, I just computed the number of bins used after phase 1 and after phase 2. Which bins are used? Which use a non-zero coordinate and some coordinate before the wave, but I'm just trying to compute. So this means that p1 plus pi is positive. This means that during the first I waves I already used these bins, and I just have to add the number of these bins matching this pattern, and I should divide it by the optimum value for some optimum value for the sigma I, and this should be smaller than t. Okay, now I'm just making some rearrangements, so it's just instead of k, I'm of course using s, x. So the sum of those x's divided by, well, not the optimum value, but the optimum value, well, if I also divided this by n, then it's fine. So that's the second type of inequality. Okay, and then I will just minimize t. So this is basically the system of inequalities which we get, and if we solve such a system, then we will get a lower bound for the bin packing. Now let's see. This is the same as we've done before, because if you just think about it, then in the previous case, so the previous case we get, okay, so I had several packing patterns, actually 4 of them. So for the first one, okay, so that's I think I'm just writing again this part b equals, so 1 0, that was the one item of size 0.4, and then I got the 2 0, which was the 2 items of size 0.4, and then I got this 1 1, which is 1 item each, and then I got the 0 1, which was for 0.61 only. And then for the first row I should just state, so it's for I equals 1 and for 2 I get separate equality. For I equals 1 I have to sum the first coordinates, that's what it says, which means that 1 times x1 plus 2 times x2 plus 1 times x1, well, x3 plus, well, 0 times x4 is alpha I, which was 2. And then, okay, so of course this is 0 times something is 0, 0 plus something is something, 1 times is not that important, so this is the same equality which we already got for the first case. Now for the second case, it's 0 times x1 plus 0 times x2 plus 1 times x3 plus 1 times x4, and this is alpha 2, which is also 2 because there were 2n items of size 0.6. so that's how we get in general these constraints. And of course this guy here is just that we have to sum, so for again we will have 2 such inequalities because there were 2 waves of the input, namely, so for the first one I'll just have to consider those tuples, those patterns which have the first coordinate being positive, so not this one. But for the other 3, the first coordinate is already positive, and I have to sum these guys, so it's just x1 plus x2 plus x3. And I just have to divide it by the optimum for the first wave, which was n, because there were 2n items of size 0.4. So that fit into n bins, divided by n, which means I should just divide by 1, and this is at most t. Now this is the same inequality which I got in the previous case, and for the second one I just have to consider all those tuples having p1 plus p2 being positive, so well, all of them, which means that it's x1 plus x2 plus x4 plus x3, yeah, all of them. But for this wave, the optimum value is 2n, divided by n is dividing by 2, being at most t, and I just have to minimize the t. Yeah. So the green is the general form, and the red is just the specialized form for this particular input sequence. But the general construction of this, and this is called the pattern method or pattern sequences, packing patterns, to be honest. And actually better and better lower bounds can be gained by choosing more and more complicated input waves. Sort of, the longer you have, well, of course there will be a longer procedure to optimize the RP's problem. So if you have, say, hundreds of thousands of waves, then it's quite possible that you won't have enough time to optimize this system. You will run out of memory, or you will run out of time, whatever. So the better the processors, the better the computers became, the larger such wave sequences can they analyze, and the current record, so the current record gained by this approach is, of course, you shouldn't know this by heart, so it's 1.5401, which means that there is no deterministic algorithm which can be better than 1.5401 competitive. So this means that all the deterministic online algorithms for the beam packing problem have a competitive ratio, an asymptotic competitive ratio larger than 1.54, and we will prove in the next video that Well, next fit will have a competitive ratio of 2, and the other guys, say first fit and best fit, will have a competitive ratio of 1.7, which is not that large, so it's just larger than the 1.54, but not that much. And if you just let the k parameter to be large enough, then it will turn out that the competitive ratio of the harmonic algorithm is slightly better than 1.7. But that's not a part of this video, but it's part of next one. Till then, bye bye.